Yeah, the presentation is called Gas Through Cracks. They're not really cracks. They're, if you like, talcs would be a better word, areas of unfrozen permafrost where the gas can escape from. The basis of the talk is to tell you how important this work is and to tell you about how I've very gratefully been resourced through a SIOS Innovation Award to develop some sort of better monitoring infrastructure for looking at this gas escape. So it's very kind of you to give me this much time to describe this. I haven't got too many slides, so I'll talk more than I indulge you in text and graphs and so on. This is a picture. Some of you know this place. This is Riverbed Pingo. It's a brilliant name for a pingo in a riverbed. But the small hill form here is one of these amazing periglacial landforms that we have, a true sign of permafrost. And you can see, it's great when you can visibly see chemistry, isn't it? Look at the color of that ice. Something's going on here. And that's what we call funky groundwater. It's deep sourced, fairly deep sourced. The permafrost might not be so thick in the river because of the energy from the river flow, but there's a lot of iron in that's oxidizing as the spring reaches the surface. And we were out there 2 days ago, and if you took a water sample, it was red, comes up clear and it goes red within 10 minutes, has a lot of gas in it. So we were able to just take water out and flame it on site, and students like that kind of thing. So I guess we'll start seeing this more on YouTube. And I'm so childish, I love it every time, and we're going to do that today. So just getting into the talk, I've been here 5 years. I'm obviously in a department that's got Hannah Christensen in, so I've learned a lot about permafrost observations and landscape. I've learned a particularly lot from people poking, scratching, sniffing and coring and measuring the landscape here. And its history over the Holocene is particularly interesting. And the top right just shows a sort of cartoon of the land system here, and with all the relevant elements to it, which make methane science quite important. Now, you might notice that Svalbard is a sort of amazing arena for marine gas dynamics. There's a few nice papers on terrestrial gas dynamics, but there's really not much at all in terms of seepage of methane from land. And of course, emissions from land directly in contact with the atmospheric boundary layer are potentially more harmful, if you like, than emissions through a few hundred meters of water where they can get oxidized. So the landscape here is something that's worth studying in this context. We're in a proven hydrocarbon system, so we've got shale bedrock. And I was going to try and get through the talk without mentioning the F word, but try and work out what you think I mean by the F word. But there's a lot of gas down there because there's a lot of shale, okay? There's a lot of gas migrating upwards. The CO2 project at UNIS was brilliant. It drilled to 900 meters or so and showed us where this gas is, what its composition is. And I don't know why I'm out of breath, actually. Something. If I'm breathing heavily down the microphone, I do apologize. But through looking at this deep profile of methane, we're able to see we quite literally got geogenic methane just slowly kind of diffusing upwards over sort of geologic timescales. And sometimes that's enhanced by things like glacial erosion and other processes. We've also got the well-known sort of near-surface methane production. Most of the literature comes from, for example, Toolik Lake region, Arbisco, and where we're looking at surface biogenic methane production by happy bugs living in a deepening active layer with access to organic matter. That's not really, I mean, this happens here, and you'll be surprised at how much methane is produced in the active layer. But we've got this hydrocarbon system that's just allowing gas into the landscape all the time. So one of the reasons we've got a problem here is that we have permafrost and glaciers to prevent the sort of gentle release of this gas. And so we have, it's been called a cryospheric cap by an eminent permafrost scientist, Katie Walter Anthony in Alaska. It's a good term. It's always good to have a bit of alliteration when you're naming something cryospheric cap. And indeed, it serves to sort of trap gas beneath permafrost and glacier ice. And then if you knock that landscape out of equilibrium by climate change, for example, you can find that you can start to degrade the permafrost slowly or make the glaciers retreat quickly, okay? And both those processes, along with some others that you wouldn't expect, allow this gas that's built up beneath the permafrost to rapidly escape to the atmosphere. So we need to put some numbers on that, and we've discovered the processes through projects run from UNIS using this amazing land system. UNIS is a great hub for permafrost. There's proper sediments here. It's not been scraped down to bedrock like some of the other really well-studied parts of Svalbard. So we've run a few projects through the Research Council and various other funding mechanisms, and now we talk about Klimagas, and Dimitri is going to probably present a poster on methane ice. And these are the projects where we look very closely at what's going on at small sites. And we need better monitoring technologies. We found the sites, we've kind of taken snapshots, now we need to really focus on what's going on. There should be some bubbling noises there. I could actually replicate that with my stomach right now. But this is just some of the examples of the glacial sites. You have to explore more than you want people to know to find all of them. It involves going to some ridiculous places. This is inside Drumbrain. This is a major channel through Drumbrain which dries up in the winter and then fills up, possibly with a little bit of water draining the glacier, because it's a big glacier, but it's not very warm at the bed of Drumbrain, even though it's big. But it takes a lot of the channel acts as a preferential groundwater flow path. So it actually builds an icing with groundwater, and in that groundwater is a lot of gas. So you can find some of the gas emission sites right next to the ice margin. This is what we did with a previous project called Klimagas, funded by the Research Council. And these are the glacial sites. I told you the glaciers retreat quickly. Their disequilibrium with permafrost is fascinating. Glaciers doing this, permafrost trying to catch up, and it's changing very slowly. But to begin with the glacial sites, we've kind of visited this area here. So we hit this hard and then visited. These are the sites we sampled. We've actually visited more sites, but the sites we couldn't sample are in red or pink, and the green sites show where we found groundwater seepage in front of glaciers that are almost all retreating. There's a few surges in there just to make it fruity, if you like. Some of the surging glaciers doing very interesting things to the gas dynamics. That's another talk. But this is the sort of wonderful region. So we've got Advent on our doorstep, an amazing permafrost observatory, and then we've got Northern Shortland and a little bit more, all within a strike range of a day from UNIS. Fantastic sort of geospatial region. There's some more noise that you're missing, but I think you can guess what that sounds like. And then it's Gabby tasting the water and finding that it's quite disgusting. This is one of our local sites here. That was her there, you just tell. But the nearest site where this is happening is Foxfauna. And this site is up, this is Brandbrain, not too far away. And this is one of the better ones. It's it's the top left black ring there. The black rings there are the concentration of methanes in the seeps. Well, after a while, you notice there's lots of little dots. Even those dots are supersaturated with methane because the equilibrium concentration of methane in water that's in equilibrium with the atmosphere is almost nothing and wouldn't show up as it'd be like a pinprick. So the size of the circle is equivalent to the concentration of methane. And just for fun, because we use units that others are using. So we're using everybody else's units and nanomoles. So that's why we go almost to 10 to the 7 nanomoles. We've got lots of nanomoles. I mean, I'm doing that to poke fun at some of the really important work going on where there's trivial amounts of methane. We've got a lot of methane here, okay? So 10 to the 7 nanomoles, what does that mean? Well, I guess 41 milligrams per litre is probably a more accessible quantity. That's how much gas you can cram into water before it absolutely refuses to be dissolved at about 0 degrees. Okay, so most of the water we're sampling is about 0 degrees because there's plenty of cooling going on when we're sampling it. So we have absolutely the maximum amount of gas possible in some of these waters. Remember, the equilibrium concentration is a pinprick on that map. So even the sites that are showing up are all a little bit, saturated. So we've got gas saturation everywhere, and yeah, all of our sites except one have got gas in. The one that doesn't is the nasty, if any of you have driven back from Mälardalen, it's that nasty glacier icing you have to drive down when you do the turn. It's rubbish, it's got no methane in it. It's the only one. It's rubbish in so many ways. So those are the proglacial sites. And this was like the big wow moment when we did this project. We've got gas leaks from virtually every glacier forefield. The periglacial ones are the ones that started the project. Look at Inner Hitapingo here, beautiful landform formed by freezing of groundwaters. Is going through these, in this case, soft shale. Freezing near the surface enables a hill form. So you've got a high pressure, they reckon about 2 megapascals. That tells you something. If you're into gas hydrates, that tells you something straight away. Anything coming out of there must have been a hydrate, solid form of gas, because the pressures are so high to form that landscape and heave it up like that. So we've got just gas flying out the top of there, probably because the hydrate is falling apart because it's getting a bit warm. And every now and then, Inner Hita weeps and gives you a little seep that comes down into the scooter track. It starts from where the people are. I think that's Dimitri at the top there. He's moderate height. The landform, is it 40 meters high, Hannah? In the Hitapingo, about 40? Oh, 20 there, exaggeration. But this amazing landform is really in peril now. It's being eroded very significantly and has nothing like this cascade of ice coming down. And the cascade of ice is caused by this constant groundwater flow all through the year. This water is coming from beneath the permafrost, doesn't care what time of the year it is, it's being squeezed up. And if we sample there, we have exceptionally high methane and CO2 concentrations. And it's like champagne. If you drop a little bit of acid into a sample to stabilize it, the CO2 goes nuts. It's like opening a bottle of champagne. So these pingos are amazing groundwater-related features in Svalbard. They're not always formed in the same manner. But in Svalbard, wherever we find a pingo that's weeping, it's a gas source. And you can see the sites there. No, you can't. I think you can see the sites there now. Yeah, there you go. Animation. I press the button and voila. The pingos are the yellow points there, so not so many. And then there's some other sorts of, not all groundwaters, of course, can partially freeze before they leave the ground and form this landform. So we've just got some that build big icings in winter, and those are in the blue there. Okay, so fewer sites, 16% of all the sites are sort of groundwater seeps, but the pingos are very special. Concentrations. So here we are in Avondalen. I need my glasses. I'm going to do it without. I just think that's the right button. No, it's not. I can't even see. Hang on. Glasses and a microphone. Here we are in Avondalen. Do you notice anything about the pingos in Avondalen? They are rather special gas sources. I can't see you now. So we've also, I mean, there's more to it actually. So, but the pingos are very significant gas release sources. Some of the groundwater springs are okay. This is the one that's Surhita, as you come out of, on the way to cross to Slapbrain, you notice there's always a big icing there. That's a good gas source too. And if you can sample it properly, you do get a lot of gas. And then we have pingos out on the east coast near the Jurassic shales that have got hydrocarbons coming out of them. It's not just gas, you can see the oil almost. And then some nice ones in the lower Rheindalen, Riepfjellbrain and Reistopdalen, and then Nipingo. Some lovely sites visited by geomorphologists at the top. And then some coastal pingos, very similar to the ones you're going to go to in Lagoon Pingo, which is this circle here later on. So the Pingos are notable then for being long established. Didn't talk about that, but they're old, much older than a glacier forefield that's just a few decades old, maybe 100 years. The Pingos could be a few thousand years old. We'll talk about that when we're out there. They're long established and they're good gas sources, drawing waters from beneath the permafrost and releasing the gas. So you put them together. You might have noticed the color scheme there. That's the geology. So the purples and the blues are looking pretty good. These are the shale units out here, but the yellows are sandstones, shales, and coals, excuse me. And you notice they outcrop again, the shales in the west. Here they're almost vertically stacked, really lovely gas migration just along the strata, straight out. And indeed, Grundfjord, Vestra or Ostra Grundfjord, two glaciers with a lot of gas in front of them. I could go in the sea, in fact I will later, and show you that the same's happening here and up here. And we've sort of sampled beneath the sea ice over here. But you see the shale units striking across here and lots of gas, and then you see lots of gas near the shale unit, actually right at the boundary with the Helvetia yellow sandstone formation. There's a shale unit right next to it. And these are carrying the Adventdalen gas everywhere. So we looked at the chemistry then. Is it the same gas? Then we realized it's not abundantly clear from the data, but you look at the composition of the methane. If you get isotopically light methane, it's biogenic. If you get isotopically heavy methane, it's either biogenic that's been partially oxidized or it's thermogenic. But we just see this tending towards lower values here with the Pingos. And that's caused by the Adventdalen Pingos, which are releasing old biogenic gas. Everywhere else is shale gas. It's really weird. Except one of the glaciers, Marmorbrain, which is one of the big circles out on the east. That's the only other site where we're getting biogenic gas coming. And we think it's old, and we think it's been there a long time because we can find no evidence of happy methanogenic microorganisms in the groundwaters. So very unusual. Mostly though, it's North Sea gas, if you like, or something equivalent, shale gas. So to give you an idea of the flux, we know the concentration, we have these snapshots, we know the concentration, we visit them as often as we can. Obviously it's difficult, more on that shortly, because that's why TerraSeep was presented for consideration for funding. But if we can measure the volume of the icing, we get an idea of the groundwater flow. And then if we measure the chemistry, concentration, we can get an idea of the abundance of methane trapped in the source waters that are forming the ice. We don't sample the ice because the gas is gone. We don't sample the water unless we think we're right on top of the seep. Otherwise, we just think the gas is so far out of equilibrium, it's pointless. So if we get good samples, we measure them, and we do that with a range of sort of chemical measurements. Has oxygen gone into the system? Is it pressurized? So on. Does it stink? Can you set fire to it? That kind of thing. So when we're happy, we take the sample, and that's why we did recover good samples from all those places. And then we measured the aerial extent of the icings using satellite remote sensing. And we ran a ground penetrating radar over as many of them as possible to get the volume from area. Quick and dirty, but those of you that know me, yeah. So the outcomes, 1 seep per 46 kilometers squared. That includes glaciers, because 86% of them lie in a glacier forefield. It's quite a lot. Study area is 6,250 kilometers squared. Lovely playground. Thanks to UNIS and the logistical resources, we can just hit this whole area. If we scale it up and use appropriate sort of Monte Carlo type simulations of uncertainty, we are in that range of 30 to 300 tons per year. And some of you will not like this, but if I scale up just at the Svalbard scale, more on this later if you like, we get to about 2,000 tons a year. If we normalize for area, about 40 kilograms per kilometer squared per year. Yeah. So that's the, those are the numbers. Is that a lot? Well, you could argue that Svalbard is equivalent to 10% of Norway's sort of what you call admissions that somebody admits to. Anyway, if Norway has got good estimates of its emissions associated with the oil and gas sector, then it's only 10 times more than what we're measuring at the moment coming out from Svalbard. It's a sort of sensationalized comparison, not too. We could have a whole discussion about Norway's alternative energy sources, if you like, but I'd have to mention the F word. The depressing comparison, those are natural seeps, about 20% of Longyearbyen's energy needs. No comment, don't know who's listening. Or 0.3% of one leak in one Russian mine that's recently been found using this new emerging satellite-based technology for detection of seeps, in mega seeps, if you like, from the atmosphere. And I won't comment on that either. It is kind of makes you wonder, should we do natural methane seepage research, or should we just target these unnecessary anthropogenic emissions? I think Russia's good for 4 teragrams a year of methane from its mines. I think it's, come forward as the world's largest methane emitter. Amusing comparison. Now, everybody, like Britain, has got a history of being horrible with and trying to blame things like cows and that for greenhouse gas emissions. So I thought, let's blame the reindeer. I mean, look at them. They're so offensive, aren't they? So then I tried to find data on this. I'd love it if there was somebody in the room who's better qualified to talk about this. That could be all of you, actually. But if you assume that the Svalbard population range is about 22,000, 22,000, I know this. Now, I checked that yesterday. And if you assume they eat lichen rather than this horrible food stuff that they get given, I think the reindeer you ate last night might have been eating food stock that makes it burp more methane. So it's good that you ate that reindeer. Because if they have a natural lichen diet, then they emit less reindeer. So somebody's put a reindeer in a box somewhere and measured this. But if you assume that Svalbard reindeer emit roughly the same amount of methane through their burps, remember, as those encased in a gas-tight box and fed lichen, then we have natural emissions of the order of 2,000 times the reindeer population. So there's some silly comparisons as well. It's good to put Svalbard on the map, though. These are not trivial. If I was a business person talking about getting funded to do the science, you want to turn up with a flux that's about 1 teragram a year across the Arctic. Once you've got that scale, then you can talk funding, and that's how, sensationalized, that's just the nature of the modern funding environment. And funders do not like hot spots and hot moments. They want Earth system science models. I was talking to Martin about this. Earth system science models that with a diffusive flux that are very amenable to incorporation of climate data and so on. But if you go around the landscape, you'll probably find somewhere, I've missed it, everybody's missed it, there's a single gas source that's producing enormous amounts of gas. And that skews all our estimates upwards. So TerraSeep is all about trying to nail down those. And we thought we would ask for money to just develop remote monitoring platforms to look for those hot moments, if you like, and the trends, of course. But if you're actually groundwater that's being squeezed out of from beneath permafrost, responding to the sea level recovery and the permafrost aggradation that occurs following that, then finding a trend in that is going to be hard, because I don't know of any trends in sea level change or isostatic recovery rates that occur that are detectable within a project lifespan. But we need to make these things and leave them there. It's not like you've seen before. So a lot of these groundwaters, they keep flowing, so they form a nice lid. That's perfect, you think, and you can instrument that lid, stand on it. But you come back a month later and the lid's like this, and then you come back another month and the lid's up here, and so on. and then bang, it bursts, and then it starts forming again. So this is the challenge. These are highly pressurized groundwater seeps that just sort of build up and crash down again. And you'll see that today if you come on the excursion. So getting observations beneath blisters continuously, because it's frozen for like 8 months. Used to say 9, now we say 8. 8 months of the year. It's quite difficult. But we had this idea to just instrument these seeps and gain information on the methane flux and the environmental conditions there, both in summer and in winter with an ice lid. Okay, so that's what TerraSeep was all about. And it's just one of those lovely smaller grants, I should say, that you get, that you enjoy more than the larger grants you get where you become a manager. It's a hands-on grant for us, and we loved it. So you can see the ebullition of bubbles in the, it's not running so well. This is the site you'll visit in summer. I thought I'd show you summer because you'll be there in the middle of winter. It's a groundwater, I'll just get my pointer, excuse me. It's a groundwater, there's a number of seeps. There's a pond here, okay, and there's a pingo here. So there's a crater in the pingo with a small pond, and then there's a pond here that's barely at sea level, and that's what you can see in this picture. You can see a lot of bubbles. This is called ebullition, and that's what you'd be hearing if the microphone and the animation was working. So there's a zone of ebullition, but the whole pond is methane rich, so there's a diffusion, that's slow, diffusive processes occurring elsewhere. So when you stand there in summer, there's a vent. There's Kelly Redeker, who's a gas giant, as they say. We should call him Venus or whatever. But he's taught us how to trap bubbles and quantify the gas flux coming through the vent that's in the form of a bubble. This is a real challenge for our project. We can measure the dissolved concentration very easily to understand the diffusion. If you use just a typical like thin boundary layer model, you can calculate diffusion and compare it to chambers quite easily. But actually measuring bubbles continuously and turning that into a gas flux is a real challenge. More on that to follow. But if you use Kelly's techniques, you can gain. This is just one summer where we're just using chambers at different distances from the center of that ebullition zone moving away. Look, it's only 2 meters, so it's only 4 meter diameter vent with an exponential decrease in the bubble production rate. Everywhere beyond there then is just producing methane through diffusion. So we need to account for that and account for the diffusion. And the message today is that the first of those is really difficult and the second is very easy. Well, not very easy, shouldn't say that, but we've achieved the latter. Here's the evidence of that. This is TerraSeep output. So we have methane in orange in all these graphs. This is methane in the water just beneath the boundary layer. And these are environmental variables like the lake level. Look, it's flooded by snowmelt early on, and then it just drops and remains pretty level. There's a little bump there. You'd think that was rain. It's not always rain. Sometimes the groundwater inflow rate does step up a bit, which we're quite intrigued by because this water is being forced there by processes that are pretty stable, steady. So there's a water chemistry change associated with that, which is revealed by the green line here, which is the salinity. That's millisiemens per centimeter. So if I was at 55, I'd have seawater. This water is coming from below sea level, which so it's relevant to mention that. But the data show that it's indeed very fresh. It's like barely any seawater ingress into the system at all. It's nearly all groundwater that's coming below the permafrost. The methane is an up and down story. This is the percent. This is a bit of a useless concentration. So that goes up to 1 milligram per litre dissolved in the surface waters of this lake, which is a very efficient emission site driven by wind turbulence. So we record the wind. Here's the wind data, turned it into a sort of component of this. The blue line, Marius, you tell me if I'm doing this wrong, but this blue line here is the up valley wind component. And so it's basically a combination of the wind direction and the wind speed. And you can see there are sort of moments where it shifts from up to down valley. Negative is down valley. That pushes the surface water away. Just check this, yeah. That pushes the surface water away from our detector, and I usually expect a return, a circulation mechanism that then brings the deeper waters back in. It's a bit like in some of these marine environments. So we have wind, we do see evidence of that. There is wind-induced circulation here, so it's not perfectly mixed. So you have to think about where you put the detector. That's one of the outcomes of this. When we did diffusion measurements anyway, we're getting about 0.4 of a kilogram per day of methane on the lake with just short-term deployments of wind diffusion. But the TerraSeep sort of diffusion model more appropriately brings it in a bit lower at 213. And that's with a sort of 70-day window of operation at continuous resolution. That's if you believe the model. There's a big literature on chambers versus diffusion modeling and so on. So we think the platform's worked. We've delivered a remote methane diffusion system. It sends the data back here to the internet. But we need to work more on how this is not really relevant to the platform, but we need to analyze more the importance of the sensor location importance. But we got good data there. So we're pleased. We haven't wasted money. This is the diffusion. I don't know what. Yeah, this is the diffusion that's come from the model. It's very spiky. The black line is the instantaneous diffusion flux, and it's very much influenced by the wind and the concentration. It's less influenced by the temperature and the salinity of the water. And you can see it's quite temporally variable. I always I'd love to know if that's real, because if you're using wind turbulence to drive a model, you're always going to see the variability of the wind in the data. Okay. When do I need to stop, Eleanor? Is it quite soon? Yeah, good. We're all right. We're on time. So the ebullition, the bubbles. This is the device I incorporated. I started looking into hydrophones, and they were difficult. Sensing noise and processing that noise and sending it to UNIS via the phone network as a gas flux that's due to bubbles, or ebullition. Very challenging. So I abandoned hydrophones connected to our logging system and contacted Tor Arne Johansson at Bergen and asked him if we could crack a peanut with a sledgehammer, which he did. He produced two seabed devices, sort of passive seismic devices with hydrophones and geophones in them. And those are here. And we connected a hydrophone and we ran it in towards the seat front and then just put a hydrophone beneath the water surface. And we started collecting data at every millisecond for 4 months, I think. It was ridiculous. These things weigh 50 kilos because you're supposed to drop them to the seabed and be able to find them when you come back. So this is why you work with students. They carried it. They're amazing, as ever. So those were the listening devices, and you can see some data there. We recorded an earthquake and lots of bubbles, but it was very slow to get the processing done so that we've got a sort of an output from this. Huge data volume. I mean, everything went wrong. Earthquakes wasn't really a problem. It was just a distraction. Nobody felt it anyway, except us. The weather's been pants, and I had COVID right at the wrong moment. So it did compromise this part of the project somewhat. But this is where we're putting the effort in now, and it's going to be very challenging to calibrate an acoustic device. Remember, it's a passive acoustic device. We're trying to keep the power consumption down. If you want to do this properly, you'd have an active, you just use a fish finder, a single beam, and just ping it, and then you'd hemorrhage, you'd need a very significant power source. And that's not what TerraSeep is about. It's about local sites with low power consumption and deployment in as many places as possible. So that's where the work's going in over the next few months. 5 minutes, yeah. Okay. So where do we want to take this? Just quickly, I've shown you this sort of glaciers and permafrost. Here they are, roughly in equilibrium, well, very much in equilibrium. If you follow the 0 degree isotherm, the little ice age maximum, that's when glaciers were healthy. Compare them to now, where they've retreated, got thinner, and revealed a forefield that's not got permafrost in. This is where we really need to be focusing our sort of efforts in understanding the fluxes. You know, we've got glaciers are, I'm going to use the F word now, glaciers are fracking the environment here. As they approach peak melt, if you like, before they retreat and become too small, they are pressurizing the groundwater and driving methane out through their forefields. They used to drive methane into the subpermafrost environment, perhaps where you end up popping out of Pingo, according to our models, a few thousand years later. We also need to start developing something as a marine platform. People don't like working here in the summer, but in winter we can walk up there and drill through the sea ice and look for methane, and we're very much finding hotspots. This is polar brain, and it's got a lovely delta here where this is all ice formed by groundwater, and then in the sea, there's a real release of methane into the fjord from below. So it's a submarine groundwater discharge point caused by the glacier, probably. And in summer, we see gas bubbles on the surface here. Fritjof brain, similar thing. The fresh water, in this case, comes out over here, but the methane's coming out here. And we think this might be just a vigorous methane ebullition zone that's not related to a groundwater drainage or the glacier, but as the glacier retreats, there seems to be a hotspot of methane release. So we really want to get our platform developed for the marine glacier margins as well, with our next application in about a week. Okay, conclusions. Svalbard's a hotspot for terrestrial methane seepage. It's certainly much more productive than the Norwegian mainland. 1 seep per 50 kilometers squared or thereabouts, according to data from the Central Tertiary Basin. And about 86% of those are in glacier forefields. Those are young seeps, but the rest are old seeps and older periglacial, associated with older periglacial landforms. So we're trying to find the hot moments and establish the trends with this remote platform so we can find the seeps. We've done that. We think we have been very successful. We don't know anyone else who's done anything like that. So now we want to do the process work and help produce the best models with a high temporal resolution platform. It looks like we're going to be okay for the groundwater flows because there's usually not too much ebullition with a groundwater spring that just comes straight out. Although it's hard to say that unless you put a chamber over it and look at the diffusion. But what we've done so far is it copes very well with the sort of dissolved methane. But we need to really solve this ebullition, this bubble making problem, because it's a big source of methane. I don't think I showed the numbers actually. For Lagoon Pingo, the ebullition flux was 2.3 kilos a day. The diffusive flux was 0.4. I should have said that. So it's quite a significant difference. But the ratio of ebullition to diffusion varies at each site. So we need to target more of these landforms, pingos, and retreating glacier margins once we've refined this product. So big thanks to SIOS for funding this, and we're really enjoying its application. Thanks a lot.